So here at the beginning of class, we had two little tests yesterday that we didn't get to talk about. Descartes' rule of signs, and then the upper and lower bound rules. Okay? I'm going to go ahead, and at the bottom of these two pages, I'm going to write out a polynomial that you could be, you probably won't be, but you could be asked to factor. Okay? So I'm writing down a polynomial that you could, probably wouldn't be, because it's probably a little bit harder than anything you're going to be asked, which is why these aren't a huge deal. But let me show you an example of one that might be kind of nasty. I was up here making it a second ago. Cubed. X plus 30. What if you're cool? Okay, from yesterday, where would we say you should start? Possible zeros. Good. And the possible zeros, remember, for the possibles, we do plus or minus. Okay, how does the fraction work? Factors of the constant over factors of the leading coefficient. So what are factors of 30? Well, 1 goes in, 2 goes in, 3 goes in, 5 goes in, 6 goes in. You guys realize you can do 5 times 6, 3 times what? 2 times what? Oh. Why is this a hard problem? Now, it might not be hard because maybe 1 goes in. Maybe negative 1 goes in. Maybe 2 goes in. Maybe negative 2 goes in. Maybe 3 goes in. Oh, stink. Hold on, factors of the bottom. Okay, so couldn't I list these all out and say, okay, I have plus or minus 1 or 1/3. I'm going to do plus or minus for everybody. 1, 1/3. 2, 2/3. Wait, where are the thirds coming in? 3. Yeah, I have to think of all the different possible combinations. So 1 over 1 or 1 over 3? 2 over 1, 2 over 3. 3 over 1, 3 over... Wait, 3 over 3? What's that? Okay, we already have that. 5 over 1, 5 over 3. 6 over 1. 6 over 3 is just going to be 2. So we already have that. 10 thirds, 15. 15 thirds is 5. We already have it, right? 30, and 30 thirds is 10. We already have it. What's gnarly about that? There's a lot of stuff that's gnarly. Now, could you just be a champ and start plugging in 1? Does it work? Plugging in negative 1? Does it work? Plugging in 2? If you plug in 1, does it work? 3 minus 4 is negative 1. Negative 50? No. If you plug in negative 1, does it work? Negative 3 minus, oh, yeah, negative 3 minus 4, negative 7. Negative 7, that'd be 23 plus, that doesn't work. 1 and negative 1, neither one works? Let's plug in 2. Pause. What did these tests tell us, and would either one help us narrow down what's going on? Okay. First of all, what's Descartes' rule of signs say? Given a polynomial in descending order, check. With real coefficients, no imaginaries, check. The number of positive real zeros, so I know the number of positive ones to look out for, is equal to the number of variations in sign, or less than that by an even integer. Okay, we're just trying to think of, okay, let's figure out from these two tests what I can tell. Positive zeros, positive real zeros. Okay, variations in sign, what does that mean? As you go through the terms, it changes sign. So this is a positive, that's a negative. There's one variation in one change in sign, right? There's 1, 2. Okay, so positive zeros is either 2 or less than that by an even integer. 2, take away 2, what do you get? 0. Take away 2, negative 2. That doesn't make sense. Negative 2 zeros. There's either positive zeros. So either 2 or none. Okay, how about negative zeros? What's the trick say? Equal to the number of variations in sign of f of negative x. Well, who's f of negative x? I guess we have to plug in, right? F of negative x. If I plug in a negative, wouldn't that still be a negative? Okay. So we have a negative. I don't really care about it. I just care about the changes in sign. So it's going to be a negative, and then if I plug in a negative? No. Squared, and then it's still a negative, right? If I plug in a negative, positive. If I plug in a negative. So how many changes in sign are there now? Just 1. Okay. So equal to the number of variations in sign or less than that by an even integer. 1 or subtract 2. Don't you get negative 1? Less than that means subtracting even numbers. Subtract 2, subtract 4, but, oh, so I know there's one negative 0, right? So if there's one negative 0, and assuming they're all real zeros, because I didn't use any imaginary numbers, how many zeros total are we supposed to have? 3. So wouldn't it need to be 1 and then 2? So right now I know one negative 0 and the rest are positive zeros. Why does that help? I could go looking through negative 1, negative 1/3, negative 2, negative 2/3. As soon as I don't have to test any other negative numbers, I can just stop with the negatives and only look for the positives. That's one way that could, does it make it super easy? No. Does it narrow down some of the work? It could. I could look through all my different factors, testing all the negatives. As soon as I find one, I know, okay, no more negatives, let's go find positives now. So it could cut down the work. What does this one say? Upper and lower bound rules. Because remember, I have this huge long list of zeros, 1 and negative 1, neither one worked. And I did it on purpose. I made a nasty one. Okay? What's this say? Given a polynomial with real coefficients and a positive leading coefficient. Do I have a positive leading coefficient?
Yes.
Good. Suppose f is divided by x minus c. So by one of these guys, x minus one of our possible factors. If c is greater than 0, and each number in the last row is either positive or 0, then c is an upper bound, meaning you don't have to think about any zeros past c. And if they alternate back and forth, positive, negative, then c is a lower bound. So I wouldn't have to go any lower. Okay? So I want you guys to just pick one for me. Pick a nice whole number. Don't pick a fraction. Pick a nice whole number. Just pick one. Not at the beginning, not at the end. Somewhere in the middle. Go. 3? Okay. If we were to go ahead and plug in 3 and take all of our coefficients, we have 3, we have negative 4, we have negative 49, and we have 30. If I was to do synthetic division, okay, 9, that'd be 5, that'd be 15, 4. Now, hold on. Is this alternating signs? So it's not a lower bound. Are they all the same sign? So it's not an upper bound. Uh-oh. Huh. Okay. So 3 didn't work using this rule. Give me another one. 5? Okay. So then I have my, what are my coefficients? Sorry, 3, negative 4. 3, 15, 11, 55. Ooh, hey, positive, positive, positive. Looking good, right? Is 5 a factor? No, its remainder is not 0. But what do I know about 5 now that all of the signs are positive? It's an upper bound, meaning I can ignore anything greater than 5. And I can say none of those are possible zeros. Adam. Yeah, it would. Thanks. I wasn't focusing. Lo siento.
Just kidding.
Right? Because it's a positive 30. Yeah? Okay. It would be nice if it was a 0. We could use him. But still, he's still an upper bound because they're all positive, right? Which means I don't have to test 6, 10, 15, 30. Is anything else greater than 5? No, that's 3 and a little bit. That's 2 and a little bit. But do you see how these tests are really for narrowing down the by hand work of a really, really hard polynomial? So it's not that they're bad. It's just I'm probably not going to give you a really, really, really bad polynomial. I mean, I could make it the whole test, but most of you want like a few other questions besides this, right? Now, could we go the other direction? Could we choose maybe something on the lower end? Because I want to show you the lower bound idea too. Let me look at my factors real quick. Why don't we try negative 5? That's not going to be very fun, though, but we could. If we were to try negative 5, we have our 3, negative 4, negative 49, and then 30. 3, and then we'd have negative 15, right? Which would end up being negative 19. And then if we multiply, that'd be a 5, carry the 4, that'd be 5. And then wouldn't that end up being positive 50? No. Positive 46, right? that'd be 80, 95. Good. And then if we multiply it, then that's going to be negative 230, right? 0, carry the 3, 23. Oh, you added down. Thanks, Robbie. Negative 200. Is this a factor? No, it's not a factor. The remainder's not 0, but is it lower bound? Yes. So what's this tell me? Since they alternate, I don't have to test negative. I did figure out you didn't have to test positive 6, but now we figured out not positive or negative 6, not positive or negative 10, not positive or negative 15, not positive or negative 30. So, I don't know. I just wanted to show you guys how this does work. I actually do have an example for both of these where we could have done it with something simple, but with something simple, hopefully you guys are taking time to go use these rules. I mean, in homework, yeah, to test them. But in something simple, you don't necessarily want to take time for this. You probably just want to go with your possible zeros and try plugging in. Like, this takes a lot of time, and it's only helpful when, to be honest, you have a huge long list of possible zeros. And so narrowing them down would help. Does that kind of make sense? Okay, so let's go ahead and go to homework. Even though we did have some examples, they were like easier examples. Let's just talk about the questions that you guys had in homework instead, because I'm pretty sure there was at least like, what, 1 or 2 problems on each of these towards the end. Is that right? Okay, so I'd rather just talk about those ones instead of giving you like new examples that are easier. So I'm going to go ahead and get rid of those examples, and let's go to our homework. So homework number 15, section 2.5. Did homework start with these crazy tests that are sometimes helpful, sometimes not? No, right? Homework didn't start there. Oh, sorry, it's 2.6. No. 2.5. Let me freeze the screen for you guys so that you can go ahead and start checking your vocab. I don't think I actually wrote down anywhere the linear factorization theorem. You would have had to go find that in your book. But that's also nice because I'm not going to have you or make you have that memorized. So that's kind of a good thing, right? Then number 8 is lower, and then upper. You would have had to refer to that test. But once again, not making you memorize Descartes' rule of signs or the upper lower bound rule. Just trying to show you how it works. Number 26, I think you guys were supposed to start with listing your possible rational zeros. The ones that you should have gotten, plus minus 1, 3, and 9, and 1/3. If you tried plugging in plus or minus 1, if you tried plugging in a positive 3, oh, gross. Who would have wanted to do that by hand? Can you guys look up here real quick? What looks easier? Or doing synthetic with 3? Okay, both. They should both match, right? They should both get a 0, but I think mental math, I think synthetic division is easier. Like plugging in 1, I can do that in my head, and I can go ahead and do that's 36 minus 28. And I'm like, oh, it's not 0. Forget 1. Like I can plug in 1 in my head pretty easily. Negative 1 gets a little bit harder. But once you get to bigger numbers, just do synthetic. You see how the book's doing synthetic. I do the little box, whatever. But you end up figuring out that, hopefully you figured out that 3 was a perfect factor. You had a quadratic left. You could either go do a modified x method, or you could have technically gone again with the possible zeros and said plus or minus 1/3 over plus or minus 1/3, and you could have kept going. And you found that once again, it got a little tricky, that 3 works again, 3 works twice, and then 1/3 works. I think factoring with the modified x would have probably been the easiest. The final zeros are 3 and 1/3, but what could we say about the multiplicity of 3? We could say multiplicity of 2 since there are 2 of them. Number 30. GCF made it a little bit easier, right? You can pull out an x from everybody. Then you just have the cubic that you're dealing with. Did you guys put a 0 in for x squared, whether you did long division or synthetic division? Otherwise, it would have messed you up a little bit. There are possible zeros. Sadly, 12 is one of those numbers with tons. To be honest, I probably would have plugged in 1. 1 minus 13 minus 12. Well, that doesn't work. But negative 1, hey, maybe it'll break up all these numbers that are negative. So negative 1 actually does end up working. So you could have plugged in and figured out it was 0 first. You could have just started doing synthetic divisions. But you do find out that x plus 1, the factor that comes from the 0, negative 1, went in, so you have your GCF, you have your x plus 1, you have a quadratic, factor it, and you're done, dun, dun, dun. Dun, dun. 38. What were the directions on letter B? Wasn't it something like using a graph to narrow down or something like that? Using the graph to check that the zeros are in the list? Was that it? Oh, disregard. Okay, they were trying to help you out just a little bit. According to the tick marks, I think we're going by 2. So if that's 8, 6, 4. If you looked at the graph, you could tell that the 4, anything with the 4 or beyond wouldn't have worked. You could have also been able to tell that the 1/2, let's see, 8, 6, 4, 2, 1, 1/2. Oh, that would have been a little hard to see. It seems like one of these is working, and it seems like one of these is working. I think 2 was supposed to work. If you guys actually kept on going and solving, you could have tried plugging in 1, -1, but according to the graph, if that's 2, there was nothing going on at 1 or -1. So you could have skipped the 1, -1, could have skipped the 4, -4. The plus or minus 2 would have been enough for you guys to be able to do synthetic division and solve. But they were just trying to show you, like, if you have a super long list of rational zeros, and if you can get a sketch of the graph, sometimes that'll help you narrow down also. But some of you are like, if we're going to our calculator, why aren't we just using the zero feature, right? Valid. On a test, if you were allowed to use your calculator, yeah, why not just use your zero feature? Unless it's a long answer and I ask you for the complete factorization. Zero feature won't cut it then. 68. Did you guys figure out it was a difference of squares? It's kind of hard. It was a 4th degree. But it is, because he can be broken down to y squared, y squared. He's a perfect square of 16 times 16. All of a sudden, life got nicer because, was this one of the ones with A, B, C, D? No, it wasn't, was it? Okay, so then you just had to factor him, y minus 4, y plus 4, and then this guy's imaginary. Can anyone remind me why? I mean, we see it, but why is it imaginary? If you set equal to 0, you're going to have a square root of a negative number. Good. Okay, 96 was testing your lower and upper bound. And I think on number 96, I can turn there real quick. Didn't they actually give you even the numbers to try? So you didn't have to go looking yourselves. Like, they actually chose numbers that wouldn't have even been in the possible list of zeros. Because the possible list of zeros were kind of slim pickings. But they said, hey, test this guy and figure out that he's an upper bound. There are no zeros above him. And check that he's a lower bound. There are no zeros below him. And so you should have been able to see by plugging in no changes in sign, upper bound. Alternating signs, lower bound. That's all you had to do. Synthetic division with the number. Show all the signs are the same, or state all the signs are the same, and then state that all the signs change. So what this means, guys, is even though there are no nice zeros to this problem, meaning the possible zeros of plus or minus 1, that's it, neither of them will work, the decimal zeros won't go below that number. Maybe it's helpful, maybe it's not. It'll be more helpful if you were able to narrow down the range, but they didn't make you work super hard for that problem. I think that was the last even. But guys, did I give you a Descartes rule of signs problem? What number was that? 80.
89.
Oh, thank you, thank you, thank you. Was that the only one I gave you?
Yeah.
Okay. To determine the possible number of positive and negative real zeros, can we just collaborate on this real quick now that we've seen Descartes' rule of signs? Okay. How do we think about, or how do we test how many positive zeros again? Do you remember? Yeah. Positive, you just consider the changes in sign of f of x. Positive, positive, there are no changes in sign. What does that mean? If everything's being added, I can't possibly have a positive number that will just make the adding be bigger and bigger and bigger. There are no positive zeros. None. Or less than that by an even number, but subtract 2, subtract 4, they're all negative. That doesn't make sense. But how many negative zeros then? Oh, well, that's easy. It's a cubic. So if there are no positive, there must be 3 negative. Why is that not necessarily true? It's possible. And why? What other kinds of zeros would there be besides positive and negative? The test says real zeros. Yeah, there could be imaginary. And if there were imaginary, there'd be a pair of them. Sorry, what are we supposed to be looking at? F negative x changes in sign. So don't we have to find f of negative x first? Okay, he's an h. All right. I'll pretend he's an f for a second. If I plug in a negative x cubed, doesn't that flip the whole sign? And if I plug in a negative x squared, why does that not flip the sign? Negative times a negative. And then there's nothing to plug in. How many changes in sign? So there's only one negative 0. There's 0 positive zeros, so how many imaginary? And that will comprise my 3. So then you know to be looking, if you're looking at all your possible zeros, only look for one negative number, forget everybody else. Which might be helpful. Unless it's a decimal and it's not one of your nice rational. Then it could be messy. But. All right, kiddos, did you have any questions beyond the Descartes rule of signs and the upper and lower bounds? Kathleen? Anything before 51? Anything earlier than 51? Number 1? Okay. So let's look at that vocab and let's go to number 51. The blank blank of blank states that if an f of x is a polynomial of degree n, then f has at least one 0 in the complex number system. I don't think I gave the name of this one. Did I? I don't think I gave the name of this one. But what did you guys find when you're looking at the section? Fundamental theorem. Oh, I did give that one in notes, didn't I? I just don't think I stated it that way. But the fundamental theorem of algebra. I stated it in a way that a polynomial of degree n will have at most, or will have n zeros. I didn't state it in the sense of at least one 0 in the complex number system. Sorry, bud, that was a little bit confusing. Number 51. 51, Tony. 35. B?
Yeah.
Okay, in number 35, four possible zeros. That's all. The rational zero test, remember that's our list of possible. I think you're talking about letter A. Take the factors of the last term, which are 1 and 3, only factors of 3. Of the first term, which are 1 and 2 and 4. And you have to do all the different possible. Yeah. And so then do all the possible pairings. So 1 over 1, 1 over 2, 1 over 4, 3 over 1, 3 over 2, 3 over 4. Anything else before 51 going once? Going twice. Sold. 51. This is the one where it has the funny directions like yesterday, right, guys? First, letter A says nice factors. Letter B says factors. And letter C says, okay, now you can go imaginary. So A says keep them nice. B says make them not nice. And C says go ahead and go imaginary. So as you guys were looking at these guys, nice thing is this guy's actually a trinomial. So I'm actually a little bit. You guys could have done the modified x method. You could have also done your possible zeros. But I see that if I think about negative 27 and 6, 9 and 3 are pretty good candidates. I'm only allowed to do this because it's a trinomial, missing the cubic term and a single x term. If it wasn't missing those, I couldn't treat it like a trinomial, an old school quadratic. But in this one, I can. Now, guess what? This is letter A. And can you guys tell why? It's nice, and I can't go any further without making it. This one I can actually factor. But is it nice? No, square root of 3, I don't know that number. It's not rational. These are irrational numbers. It's still possible, keeping it real, but keeping it real with irrationals. That's letter B. And then letter C says you don't have to keep it real anymore. And how does that help? What can I do with that x squared plus 9? Sorry. Yeah, I go imaginary. And I can say x plus 3i and x minus 2. You go to factor, you can set each of these equal to 0 since they're little baby quadratics without middle terms. But that one's plus or minus root 3. I had to wait until letter B, until they said you can go irrational. And then this one I had to wait until letter C. They said just factor it all together. Or all completely is how they said, sorry. And that meant you can go imaginary. Okay, anything else? All right. Some of you guys, you might have more questions than this. If so, come on in. If you don't feel comfortable asking in class, that's okay. Come on in after school. I'll be here today not very long, only until like 3:15, but that still gives half an hour after school. Or during lunch, I'll be in here if you need me. Kiddos, let's go ahead and go to section 2.6. I did have a warm-up, but I think we ended up warming up with Descartes' rule of signs and the upper-lower bound, so I'm just going to keep going. To section 2.6, rational functions. If you guys remember, and maybe you don't, go look at your table of contents really quickly. You should be updating that anyway since we're getting close to the end of chapter 2. Maybe you might want to go check out your class calendar on my website, tinyurl.com/duecmath, to see when the test is. Whenever a new chapter starts, I pretty much do the calendar up until the next test. But if you remember, the very beginning of chapter 2, what was the title of chapter 2? Polynomials and? Okay, we've spent the first sections on polynomials. Now it's time to go into rational functions. Let me give you guys a second to go ahead and start on notes. I'm checking out the calendar to make sure that I'm keeping us on track with what we're supposed to be doing. And so I can put up a due date on your guys' homework. Okay, news, I don't have the homework due Thursday, but careful. I have section 2.7 due on Friday, and that is the final section of this chapter. Meaning there will be a test next Monday or Tuesday, depending on how the rest of the week pans out. Just in time for you guys to take your PSAT next Wednesday. I think that's the PSAT. Rational, ratio, fraction. Oh, it's a polynomial over a polynomial. It doesn't have to be a polynomial over a polynomial, but at this level, that's all we're going to be worrying about in the top bottom as we go through the rest of the course. Maybe we'll end up with trig top bottom, or exponential e to the something top bottom, or logarithms top bottom, but for right now, just polynomials top bottom. Polynomials in a numerator, polynomials in a denominator. Denominator! When a denominator comes, what do we have to remember? We have to remember that we're all of a sudden going to have domain restrictions, right? Polynomials, domains were all real numbers. Forever left to forever right. X was negative infinity to positive infinity. No domain restrictions. But rational functions, definition of a denominator, not definition. Definition of a rational function has a denominator. Oh, he can't be 0, right? So we're going to be looking for, you guys know this term? Discontinuities, aka values of x that make the function undefined. Values of x that make the function undefined, discontinuities. So guys, what's my domain for the example down below? You guys remember how to do this, right? Denominator can't be 0. Denominator can't be 0. X plus 2 can't be 0, which means x can't equal. Now, some of you might have been thinking interval notation, and if you were, that's okay. I'll show you what it looks like. But I was just looking for the short, sweet version of the domain. You have to go up to -2, but not including, and then you have to go past -2, but not including. Do you see it? That's how we exclude -2 from the domain. Up to -2, not including, past -2, not including. But x can't equal -2. So, is x a discontinuity? Yes. What type? Graph it real quick. What's 1 over x plus 2 look like? What type of discontinuity is x equals negative 2? Can you tell from the graph? Some of you amazing ones might be like, wait a minute, that's 1 over x shifted 2 to the left. I should remember 1 over x from section 1.6, parent functions. But for the rest of you guys looking at the graph, this is not just any discontinuity, this is a vertical asymptote. What other types of discontinuities are there besides vertical asymptotes? Remember this guy? Nope, it's not a 0. It's a hole. You have to figure out the difference between who's who. So, 2 different types of discontinuities and 2 different functions that show you the 2 different types occurring in their natural habitats. Well, something like that. 2 different types of discontinuities show up in rational functions. So when you have denominators, they're not allowed to equal 0, but those zeros of the denominators can be 2 different things. If you want to grab out your phone, Austin, I'll go back to page number 1 for a second. We're on page number 2. Ready? Got it? Okay. So, rational functions, denominator cannot equal 0. But 2 different things can happen, or 2 different types of discontinuities can happen. I want you guys to go ahead and, once you have them written down, find me the domain of each function. Find me the domain of each function. And I want you to do something crazy. Okay? I want you to find the discontinuity at x equals a. So figure out, basically, this is when x, or the a's for which in rational functions, the a's will always be the guys that x is not allowed to equal. Okay? The domain for both of them. This is what's similar. Rational functions, you look in the denominator. It's when the denominator cannot equal 0, so you're going to end up with x or t or whatever your variable equaling a number. I want you guys to go ahead and plug in that number. Now you might think I'm really silly telling you to plug in that number. But I want you to plug in that number. Whatever x is not allowed to equal, or t or whoever it is, I want you to plug it in before you do anything to the function. Plug it in the top, plug it in the bottom. And then I want you to go back to the example that we just did and do the exact same thing. Go back and plug in that vertical asymptote. I want us to see any patterns. Go back, plug in, and I want us to see if we can see any patterns. I'm going to go ahead and sketch the graph over here also. Ooh, that shouldn't have been an f of x. That should be an f of what? Who are my variables in this guy? T's, right? guys can check it on your graphing calculator. I'm pretty sure that's pretty close to the graph of that guy. Anyway, coming back. Your goal right now isn't necessarily to be able to get these graphs. I was just trying to show you graphically the difference between a hole and a vertical asymptote. Wait a minute, where's the hole? Did you guys already figure that out? What x value has the hole? -1. How'd you figure that out, Adam? What'd you do? Yeah, because what can the denominator not equal? So then when you solve. Okay. What did I tell you guys to do with that number, whatever you found? Plug it in. So what I wanted you to do was plug in -1. Do you guys see that you would have gotten 0 over 0? So -1 does make the bottom 0, but ironically enough, it actually makes the numerator 0 also. Now, what was your domain down here for this guy, for the vertical asymptote? Good. 2 plus x couldn't equal 0, so x couldn't equal, once again? So then I wanted you guys to plug it in, right? What happens when you plug in -2? Careful. 7 minus 4? 3 over 0. Do both of these guys make the denominator 0? Yeah. But one makes the top 0, the other one. I want you guys to go back to this guy who had a vertical asymptote. Go back. No. Where's the first page? There he is. And plug into this guy. What happens if you plug in -2? Does anybody try that? What'd you get? Guess what? A quick little trick of vertical asymptotes and holes, a quick little trick, is that holes will always get 0 over 0 if you plug it in. It's a 0 of the denominator that also makes the numerator 0. And vertical asymptotes will always get you numbers over 0. Who knows what number? Could be a 1, could be a 3, could be a -pi, could be a 113. Doesn't matter. Vertical asymptotes will always get you a number over 0 when you plug in. It's just a trick. And holes will always get you 0 over 0 when you plug in. Trick, but believe me, this comes back in calculus in big ways. It's kind of helpful to figure out the trick now and to start using it. So 0 over 0, the hole, we're actually going to eventually say keep going because you can actually find the point of a hole by keeping going. Vertical asymptotes, there's no point in keeping going. It's going to cause a huge old disruption in your graph. Now, that's a trick. That's just a trick. Here's another way of looking at it. And this has to do with the name removable discontinuity for hole versus non-removable discontinuity for vertical asymptote. There is another way of thinking about this besides the trick of plugging in. And the other way is that your denominator for holes can always factor out. So you can actually take this function and rewrite the numerator with factoring. And what's always going to happen with a hole? There's always going to be a shared factor. That's what the 0 over 0 stands for. There's a shared 0, a shared factor. And the shared 0 and shared factor, if you can find it and identify it, you can reduce, you can cancel away. So did anybody figure out before I got here, or do you see now how I got the graph of this guy? I, in my head, factored this out and said, hey, this is the exact same thing as just t minus 1, aka a line with an intercept of -1, -1. This is just, t minus 1. Bummer, guys. Did I graph it right? No. What did I graph wrong when I did mental math real quick before? I made the slope what? A negative number. What's the slope supposed to be? Positive number. So does my line still have an intercept at -1? Yeah. Does it still have a hole at not y equals -1, but at x equals -1? Yeah. But my line's supposed to be going up. So question, where's the hole at? How can you find the position of a hole? Take away the shared factor and then plug in and say, hey, the actual graph who has the hole, where would his point have been? So you could go ahead and plug in and then say, oh, well, if t is -1, after you take away the hole, it would have been at -2. So that's how you can actually graph a hole. It doesn't exist in the original function, but once you factor out the hole, then you could go ahead and plug in and find the point and say the hole is at x equals -1, y equals, plug it in, -2. So this whole factoring out thing isn't helpful just for getting the graph of your function, but it's also helpful for finding the hole position as well. Now, vertical asymptotes, how did I get the graph of this guy? Oh no, I had to review things like a horizontal asymptote. I had to review things like x-intercepts. Ooh. So maybe we have some more rational function work to do, right? And maybe a few more calculus-y things along the way as far as notation. But we'll get to that tomorrow. So you guys can start this homework, but definitely not finish it. Not yet. Bye, cool kids. Good work today. I'll see you guys tomorrow. Unless you need to come in and ask me questions, you're more than welcome to.